Students, welcome to lesson 8.1.1. Chapter 8 will be the last chapter that you're going to cover this very strange and unique spring. The objective today is to combine a horizontal stretch and shift of the same trig function. So we're going to be moving our trig function left and right. That's going to deal with the b times x minus h, and we're going to try to understand that a little bit better in today's lesson. Laurel and Hardy are trying to write the equation of a sine function that has a graph with a period of 2 pi divided by 3 and a horizontal shift of pi over 2 units to the right. Laurel thinks the equation is sine of 3 times in parentheses x minus pi over 2 and parenthesis, but Hardy thinks it is sine parenthesis of 3x minus pi over 2. Who is correct? What is the difference between these two equations? How do each of these equations transform the graph of y equaling sine of x? Now we're going to try to examine that over the next couple slides, but let's start talking about what's taking place right here. We have the sine of 3 times x minus pi over 2. Now this minus pi over 2 on the inside, that's going to end up shifting our graph pi over 2 units to the right. Then this 3 is going to, that's the b value. The b value is 3. So that means the period is going to now be 2 pi over 3. Well, let's look at Hardy's equation. This says minus pi over 2. And there's a 3 out in front. So that means b is equal to 3. And the period then would be 2 pi divided by 3. But there's a difference. This one has an extra set of parentheses. In other words, it is really 3 times x minus 3 times pi divided by 2, where this is just 3 times x minus pi over 2. Now, which one is really going to shift it pi over 2 units to the right? Because they both are going to give you the period of 2 pi over 3. So what I'd like you to do is to pause this, go to your calculator, and graph each of these, and then come back. So please pause it. Okay, welcome back. I have two graphs, one for each equation, one for Laurel's equation, which is in red, and one for Hardy's equation, which is in blue. When you are talking about comparing the sine function and looking for this horizontal shift, we're trying to figure out, is this x minus 2 in parentheses times 3, or is it 3 times x minus pi over 2? In black, you see your sine function. This is your influential point. It's 0, 0. That sine function's crossing the x and y axis at 0, 0, and it's making one cycle in 2 pi. The red graph, starting up here at a maximum, almost looks like a cosine, but it's not, and it's completing 1, 2, 3 cycles in 2 pi. That's where that 3 comes from. That 3 right there tells us we have 3 cycles in 2 pi. Our tick marks along the x-axis, each tick mark is a pi over 4. Now let's see what we have over for Harold's equation. Again, in black, the sine function. Now the blue function starts at a minimum on the y-axis, and it also completes 1, 2, 3 cycles. So our value of 3 the b value equaling 3, meaning that there's 3 cycles in 2 pi, is satisfied. But what about that horizontal shift? Again, the tick marks here are pi over 4. So let's use that influential point of 0, 0. Where is that being shifted? Now that's from a min to a max. We're increasing in the sine function, and we want to see where that 0, 0 gets moved to. In red, it's moved to right there. Well, that's pi over 4 and another pi over 4. So that has been shifted over pi over 2 units. In the other graph, this has only been shifted over a little bit less than pi over 4. And so that amount actually is about pi over 6. So this has a shift of actually pi over 6 units right. And the first graph has a shift of pi over 2 units right. Meaning, which equation is correct? Is Laurel's equation correct or Hardy's equation correct if we're looking for a horizontal shift of pi over 2 to the right? If you said Laurel's, you are correct. You get a star for today. So now on this page, we're going to take another approach to why this is. To understand why Laurel and Hardy's equations create different graphs, think about what it means to have a horizontal shift and the order of operations. So examine Laurel's equation. The sine of 3 times in parentheses x minus pi over 2, end parenthesis, for what value of x does that stuff inside the sine equal 0? And what is the horizontal shift of this graph? Note that this is asking for when the input for the sine is 0, not where the sine equals 0. So let's solve this for x. Let's take and divide everything by 3. 3's cancel, and 0 divided by 3 is 0. So now we have x minus pi over 2 equaling 0. And now let's add pi over 2 to both sides. Oh, wait a second. Isn't that our shift that we wanted? Pi over 2. And x equals pi over 2. Now consider Hardy's function. Where is everything inside the sine equal to 0? So start by adding pi over 2 to both sides. We now have 3x equaling pi over 2, and now multiply by 1/3, and x equals pi over 6. So what this is telling us is if you want to find the horizontal shift, take what's inside the function, set that equal to 0, and solve for x. Now the graph of y equaling sine x is stretched vertically by a factor of 2, makes 3 complete cycles in an interval of 2 pi, and is shifted up 4 units and shifted to the right. Write in shifted to the right, pi over 4 units. So I'm going to start by writing y equaling a sine of b times x minus h, the horizontal shift, plus k, the vertical shift. So h, horizontal shift, k, vertical shift. A is your amplitude. And B equals 2 pi divided by the period, or the number of periods in 2 pi. So let's start identifying this. Stretched vertically by a factor of 2. A equals 2. Makes 3 complete cycles in 2 pi. B is the number of periods or cycles in 2 pi. So B equals 3. Shifted up 4. Vertical shift, K. Equals 4. And shifted to the right, pi over 2. So just pi. We've identified our 4 transformations. Let's put them into the equation. Y equaling 2 sine of 3 times x minus pi, n parenthesis for that one, n parenthesis for the sine function, plus 4. All right, now we're given a graph. What I would like you to do is to pause this, take a look at this graph, identify these 4 transformations, and use those then to write an equation, and then come back and check your work. Okay, welcome back. The amplitude is in blue. If you take and draw a new midline in red, you'll see that the amplitude happens to be 2 units. Horizontal shift, that's that little green arrow in here. Remember, the sine function crosses the y-axis on an upslope or on an increase, and so that's being shifted over pi over 2 units. Vertical shift is the red K, that's down 3. And our period, well, it looks like 1 complete cycle is completed in pi, so our cycle or period is pi. So B is 2 pi divided by pi, or B comes out to be 2. And then put them in to write your equation. Now we're going to take and identify these and try to make a graph from them. So sketch a graph for the following function. Amplitude stands out. A equals 3. The horizontal shift is right here. And so H equals a negative 1. Because remember, it's x minus h. The k value then equals a negative 2 because we're shifting down 2. So that's your vertical shift. And that pi is your b value. B equals pi, which means the period of our new function is 2 pi divided by pi, which gives us a period of 2. Let's use those things to graph the cosine function. So here's my x-axis, my y-axis. Let's go 1, 2, -1, -2. And I'm actually going to count these by ones also. 1, 2, 3. Starting, I like to use the horizontal lines to create graphs in the midline. Since there's a vertical shift of down 2, my new midline is right at 2. And since the amplitude is 3, that means I'm going to be 3 units above that because the regular amplitude is 1. This is 3, so it's actually 3 times taller. It's being stretched by a factor of 3. And so this is going to represent my max. This is representing my midline. And then times 3. So we go 3 units below. And this is my minimum. So we've got the K and the A somewhat taken care of. But now we got this horizontal shift of 1 unit back. So the cosine normally starts at a maximum on the y-axis. Well, that maximum is no longer going to be right there. It's going to be shifted over 1 to the left. That's where I'm going to be starting my graph. And my period is 2. So I'm going to have to go down to a minimum and back to a max in 2 units. And again, down to a minimum, back to a max in 2 units. That means between a max and a max, I have to have a minimum. Between a max and a max, I have to have a minimum. And then if my period is 2, there's a max, another max, and a minimum. And so the graph is going to look something like this. I can't see what I'm doing with this stylus. Maybe I can do that a little bit better. When you do this on a test, please take the time to zoom in, make it accurate. I'm actually going to choose a different color. I'm going to go with green to connect these. And now zoom out. And there's our 3 cycles of our graph. We want you to do one. Pause this and then come back and check your work. Okay, welcome back. And taking this equation over here, A happens to be 2. Horizontal shift is pi over 2. There is no vertical shift. B is 1/3. So 2 pi divided by 1/3 gives us a period of 6 pi. I did all of that work before I started labeling my axes. Since my period is going to be 6 pi, that means I'm going to make 1 cycle in 6 pi. So let's count by pi over 2's. So each blue or red tick mark is a pi over 2. So that's pi, 2 pi. Let me start over. Pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. And then counting backwards, pi, negative pi, excuse me, negative 2 pi, negative 3 pi, negative 4 pi, negative 5 pi, negative 6 pi is way at the end for me. Now my amplitude is 2, so I'm going to draw a maximum dotted line up top representing my max. And a line down below at -2 for my min, because I have no vertical shift and an amplitude of 2. This horizontal shift of pi/2 units to the right, that means I'm going to be taking the sine function that normally crosses right here, and I have to shift that pi/2 units, which is 1 tick mark. And now apply this cycle being 6 pi, or the period being 6 pi. So if I'm at pi/2, and if I add 6 pi to it, I'm going to end up over here at 6 pi plus another pi/2. So that's where I got those 2 points. Well, if my cycle is 6 pi, then half of a cycle would take 3 pi. So I'm going to go from here, count over 3 pi, pi/2, 1 pi, 2 pi, 3 pi, and put a dot there. And somewhere in between these 2 x-intercepts, I need to have that first maximum. And somewhere between the second set of x-intercepts, I need that minimum right in the middle. So if this is going to be 1, 2, 3, 4, 5, 6 units wide, count in 3 and go to your max. Count in 3, go to your min. Now understand, we're trying to do this without a calculator. Counting back 6 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, that's going to be the end of a period. And right in the middle, when I hit 3 pi, that's going to be halfway through my period. And then halfway through these 2 x-intercepts, I need a minimum. Halfway between these 2 x-intercepts, I need a maximum. And then connect your dots. I'm going to start here and draw the first cycle. And then the second cycle. Here's your math notes on the general equation for sine functions. Hope you enjoyed this video, and I wish you all the best in this last chapter.